Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to introduce you to a concept called electric potential. However, before we talk about electrical phenomena, I want to go back and think about a Physics 1 concept a little bit, gravitational potential energy. So in this picture, what you're looking at, imagine here's a picture of me here with my cup of coffee. And if we were to consider the potential energy of that coffee cup, the first thing we would do is we would put a datum in the problem. So I'm going to go ahead and do that with my little tool here, and I'm going to go ahead and angle that. Now, you can put a datum anywhere you want, but I'm going to go ahead and put it at really ground level, and I'm going to color that blue here. So here's the datum here for measuring the potential energy. Right now, the cup is at a certain height here, from the datum, which we would measure or call h typically, and then we would say, all right, well, the potential energy of the cup is equal to mgh, and this quantity is positive if we are above the datum, 0 if the cup is at the datum, and negative if we're down below the datum. Now what I have here in this picture, imagine this is a hole in the ground. So if I actually put the cup down here somewhere and I still measure potential energy with respect to the blue datum, it's going to be a negative number. All right, now I'm going to make a little algebra substitution here. I'm going to say we're going to let this capital letter V here equal the product G times H. So this equation now is going to read the potential energy is equal to M times this thing that I'm calling V. Now, it's pretty easy to rearrange this and say that V then is equal to potential energy per unit mass, or potential energy over M. So it would have units of joules per kilogram. And that quantity, energy per unit mass, is called potential. In this case, it would be called a gravitational potential. And here's how it would be calculated, G times H. So if I were to actually calculate values of that, notice it depends on h, the height. If I pick a spot 1 meter off the ground, like right here, and I calculated a numerical value, G times H would be about 9.8 meter per second squared, or Newton per kilogram, depending on which unit you like, right? Times 1 meter, and I get we would get a value of about 9.8 joule per kilogram. So if I come over here, as long as I'm 1 meter off the ground, I'm going to get the same value, 9.8 joule per kilogram. If I'm over here, 1 meter off the ground, again, I'm going to get the same value, 9.8 joule per kilogram. In fact, anywhere on this line, let me draw the line, as long as I'm anywhere on this horizontal line, I'm going to go ahead and maybe color code this green here, I would be at a potential of about 9.8 joule per kilogram. Now, if my cup is a meter higher, say 2 meters off the ground, and I calculate G times H, where H is 2 meters, I think we get 19.6. We'd be at a potential of 19.6 joule per kilogram. And I could actually draw another green line here and actually label it. That potential is going to be 19.6 joule per kilogram. The first potential was 9.8 joule per kilogram. If I go ahead and go another meter higher, that will put us, roughly right here, and I calculate the value of the potential there, it would be G times 3 meters, and I think I get about 29.4 joule per kilogram. Right. Now, if I come to this blue line here, remember that's my datum, H is 0. At that point, we'd have a potential of about 0. All right, now imagine that we come down here a meter below the datum. If I calculate a value for the potential now, we're going to get a negative number, and it would be negative 9.8 joule per kilogram. And just for kicks, let me come down about 1 meter lower. Down here, roughly 2 meters down below the datum, we would be at a potential of about negative 19.6 joule per kilogram. So this quantity called potential, it describes energy per unit mass. Notice that it decreases as I move down. It has a datum just like potential energy. And it's just a different way of thinking about potential energy. Rather than thinking of it as mgh, I can think of potential energy as mass times potential, where this potential is the property of this space here, right? What's happening is, because we have a gravitational field, masses within that field will have a potential energy, and they can be described with this quantity called potential. Notice that if we move up into the field, we are increasing in potential. If we move down with the gravitational field, we are decreasing in potential. If I moved like left to right, there's no change in potential. Now I'm going to make a completely another video about this later, but this green line here, I can move anywhere along this line and I would be at a potential of 9.8 joule per kilogram. And this is a three-dimensional problem. It's kind of hard for me to draw, but imagine coming out of the screen towards you or into the screen away from you. As long as you're 1 meter off of the ground, the potential would be constant at 9.8 joule per kilogram. That gives you this horizontal surface, and where that surface is all at the same potential, 9.8 joule per kilogram. And that surface is called an equipotential, a surface of equal potential. Now, we don't use the gravitational potentials extremely often. In upper level classes you might, but typically in a college physics or a freshman or sophomore level physics class, we usually don't use the term potential much in gravitational problems. We usually just use the term potential energy calculated by MGH, or if gravity's constant, we would use Newton's law of gravity to calculate potential energy terms. But in any case, we don't mistake potential energy with potential, because they're different things. Energy has units of joules. Potential, in this case, gravitational potential, has units of joule per kilogram. And to point something out, like this point in space here, it's just that. It's a point in space at this potential measured with respect to the datum. There's no object there. It doesn't really make sense to talk about force or potential energy. Now it would if I put my cup there. If I take my cup and I move it over there, now we could say there's a gravitational force on the cup equal to mg, and we can say that the cup has a potential energy equal to mass times the potential at that location. So that's a little bit about gravitational potentials. I want to now talk about electric potentials. So I'm going to get a new picture here. Save this? No. All right, so now imagine that we have a positive charge here. And let's imagine it's a point charge, and let's say the value of that is plus Q. Imagine that this charge is kind of nailed down, and it can't move anywhere. Right? Now imagine that I put a small positive charge right there. Now, it's important to realize that if I release that small guy from rest, it will accelerate away in that direction, and it will leave the area with a certain kinetic energy. Therefore, the system has a potential energy as it sits here. There is some potential energy term at this point. Let me write that in black. Now, if I take this charge and I place it here, equal distance away, it's important to realize from the symmetry of the problem, if the distance between this charge, again placed at this point, and this charge is the same, the potential energy should be the same. And in fact, if I come over here, same distance, we should have the same potential energy. If I come down here, same distance, same potential energy. In fact, if you think about that, I should be able to put that charge anywhere on a spherical surface. Give me a moment here to create a circle here. Move this thing and center it. I should be able to put that charge anywhere on that surface. And let me color that blue. And it should have the same potential energy. And it's important to notice that this surface is a sphere. It's a three-dimensional type of beast. All right, now let me get rid of these. That dot wasn't perfectly in place, but I think it was good enough to get the point. Imagine this kind of imaginary sphere now around this charge. I should be able to take this positive charge, put it anywhere on the surface of the sphere. Again, it's a three-dimensional surface, and that charge should have the same potential energy. Right? We can define now what's called an electric potential. And electric potentials usually is denoted with the letter, this capital V here, and here's how it's defined. It's defined as potential energy per unit charge. So the units on electric potential would be the joule per coulomb. And like most things in physics, the joule per coulomb has its own little pet name. 1 joule per coulomb is defined as 1 volt, or I'll just say called 1 volt. Now, it's important to realize this thing called potential, it's a property of space. It's a property of the space around this charge, and it's created because this charge has an electric field around it, and that electric field will do work on, other charges placed within its reach here. Now, if I go ahead and we imagine moving inward, right? So imagine this circle being smaller. I'm going to go ahead and do this one in blue as well here. All right, there's another surface here where the potential would be the same anywhere on that surface. And if I move inward, right, there's another surface where the potential would be the same. If we move outward, there's another one, and so forth. So these would represent three-dimensional surfaces where the potentials are constant. Again, it's really important to recognize this is a three-dimensional phenomenon. I'm going to try to give that outer surface a sense of that it's 3D here. Right? All of these really are three-dimensional surfaces, and they're all at certain potentials. So I might come to this inner one, and I might call this potential 1, and this one potential 2, and this potential 3, and this potential 4. Right? It's very important to realize which potentials are higher. Potential 1 is the highest potential there. Right? Potential 1 is greater than potential 2, which is greater than potential 3, which is greater than potential 4. Now, to understand why, which ones are greater, it's important to realize what the electric field lines look like in the space around that charge. So I'm going to go ahead and draw some of those electric field lines. Remember, the field lines radiate outward from a positive charge. They're symmetrical around a point charge. So I'm just going to sketch a few of them. Get these in here. So the field lines around a positive point charge look something like this. And although they're not vector quantities, they do have a direction associated with them. They're outward. So hopefully you've watched my video on electric field lines. And remember in my gravity example, in fact you can even go back and look, remember that as we moved lower, we were moving towards lower potential. In fact, remember the hole that I built. When you move down into the hole, the potential would be negative if you measure with respect to the ground. So the big rule there was that when we went down, we were dropping in potential. When we went up, we were increasing in potential. When we moved sideways, there was no change in potential. So the same thing's happening here. If we move along this field line, we are moving with the electric field and therefore dropping in potential. If we move this way along the field line, we're moving up into the field, and hence we're moving towards higher potential. See how that's why potential 1 here is the largest potential of the ones I have drawn. Anytime you move with the electric field, you are dropping in potential. And when you move against the electric field, you are going up in potential. Another thing I'd like you to notice is that you notice that the radius of the spheres that I created are changing. All right, let me talk a little bit about why. First, let me just talk kind of in an algebraic sense. If the electric field is constant, the difference in electric potential is equal to basically field strength times distance. Now, here the electric fields are not constant, but if we think of this just kind of in an average sense here, in this region, we're close to this charge, the electric field's relatively strong. So this would be fairly strong. So it takes a very small distance to get a relatively large change in potential. As we move further out, now the field's a little weaker. So this is a little bit weaker. So if I want the same change in potential, the distance between them has to be a little bit larger. So as we get further out, the electric fields are getting weaker and weaker, therefore you need a larger distance to make up the same potential difference. I'm going to get rid of this charge in here. We don't really need this guy anymore. All right, so again, let me talk about one more time what electric potential is. Well, this is how it's defined: potential energy per unit charge. And it's important to note that it tells us, therefore, about potential energy. So just to make up an example, if potential 3 here I knew were, just to make up a number, let's say potential 3 was, say, 6 volts, or remember that's 6 joules per coulomb. That means if I put a 2 coulomb charge in that location, it would have a potential energy of 6 volts times 2 coulombs, which is 12 joules. So what it would tell us is the potential energy of that particle. Again, remember, a volt is a joule per coulomb. So I think that's probably enough about electric potential. I mean, that's what it is: potential energy per unit charge. It's important to realize what's causing it. You have electric potentials anytime you have electric fields. The relationship between potential and electric field, very important, and I'm going to make more videos about calculating potential differences. For now, for the purpose of this video, the really important thing is if I pick a point here, if I move with the field, you are dropping in potential, moving towards lower potential. If we move against the field, we are increasing in potential. And if we move at a right angle to the field, there's no change in potential. And again, that surface that you would get by moving at a right angle to the field has its own special name. It's called an equipotential surface. So I hope this video helped give you some sense of what electric potential is and why it's important. Again, it's an energy concept. It's linked to potential energy, and hopefully you've had enough physics now, especially if you've had it with me, you know how important energy concepts are. Seems like we're talking about them all the time. So anyway, have a great day.